Okay, welcome back. Today's our last lecture on parameter homocopies. What is a parameter homocopy? It's just moving the solutions to some parameterized polynomial system from one set of parameters to another parameter. Okay. And we recast the multivariate homotopy continuation algorithms we've talked about and the univariate homotopy continuation algorithm we talked about in light of this parameter homotopy as these total degree homotopies from the Bezier or the total degree start system to your target system is really just some one-dimensional path in some huge dimensional parameter space. Okay. And so we had total degree allows us to solve any system by tracking this Bezier number many paths. And by solve, I mean compute numerical approximations for all the coordinates to isolated regular solutions. In sparse polynomial systems, and the generic number of solutions there, which were isolated regular, was and away from the coordinate hyperplane, so in C star to the n, was mixed volume of these supports that give the sparse family that you're looking at, right? And so one thing I want to address is I get asked more often than you would think whether or not every polynomial is a sparse polynomial. Okay, yes, every polynomial is a sparse polynomial with respect to its own support. Okay, so being a sparse polynomial is a meaningless thing mathematically. Every polynomial is a sparse polynomial. When we talk about sparse polynomials, we're giving the implication that we're considering a polynomial system within a particular family. Which family? The family where the support stays the same, but the coefficients can wiggle around. So that is what we mean by sparse polynomial systems. We really mean a family. And same with the total degree. We really mean families when we're talking about parameter homotopes. We're talking about families of polynomial systems, not individuals. And this gives us an understanding of the members of this family in the context of the whole family. And the whole family might have a lot of structure, which we can then infer things about the specific member of that family. That's the idea. Okay. Because indeed, if somebody gives you some polynomial system, you can stick it in either of these. Now, there's one big difference from an algorithmic point of view between these two families. The total degree family has an easy to solve system, which has the right number of solutions. Okay. Inside here is the total degree start system. But in the sparse polynomial system, it does not appear that there's such an obvious choice for a particular instance, which is easily solved. So for example, if this system has Bezier bound 1000, but BKK bound 11, and the true number of solutions is 7. And this situation, by the way, happens more frequently than you would think. It seems right now, if you've been paying attention to the class and following everything, that the only way we could solve this is by actually computing 1000 homotopy paths and just ignoring the 989 of them, which go off to infinity. Okay. And that's an enormous waste of time, right? And this is actually a pretty mild gap between the number of, sorry, the 993, which would go off to infinity or do some other bad stuff at the end. And that's a pretty actually mild gap. In reality, you do see this gap get really, really enormous. And when talking about computational cost and computational complexity of solving a system via numerical path tracking, a very common measurement of that complexity is the number of paths needed to track. Okay. Okay. Great paper by Huber and Sternbals. Which outlines a so-called polyhedral homotopy. So you would love to think that these two authors, for any collection of supports, so any collection of like Newton polytopes, they were able to just identify a specific instance whose solutions were obvious. That would be the most naive way you would try to generalize this total degree star system polyhedral case, but that's not what they do. They're actually using some tropical methods that I'm not going to explain in this course. Okay, but I can tell you features of the algorithm that might just give you some insight what's going on. So we have the incidence variety of all polynomials and their solutions, where the polynomials have support a bullet. And this is a mixed volume of a bullet to 1 map down to the parameter space, which I'll just write like this. Obviously, a bullet is not a number. When I write this, I mean the number which is the number of coefficients appearing in the whole family. And the question is like, okay, well, how do I get the solutions over just a random point here? And what they do is they do this trick, which is a common trick in algebraic geometry, which is that they're going to deform these coefficients in some extremal way so that the solutions break up into buckets which are all easy to solve. Okay, so there's going to be some very extreme path that they consider. And it's almost certainly going to land on the exceptional set. Okay. Which means these paths, they go off to infinity really, really fast. Some might be finite, sure. And then some of them might leave the solution space in the sense that they still stay finite, but they don't stay in C star to the n, which is the setting of BKK. Okay, so that's another way to kind of leave the solution set. Okay, and so strictly from the combinatorics of the supports and the polytopes, one can see how many solutions are going to certain parts of your space. How many solutions are going to infinity in this way? How many solutions are going to infinity in some other way, etc. And you bust up all your solutions into these buckets. Okay. You reparameterize the solution space so that infinity is no longer infinity. Don't worry about that. So if you know about projective spaces, you're taking a different affine chart. If you don't know about projective spaces, really don't worry about it for now. So they choose new charts so that things approaching infinity become finite points, and then they just track back just a little bit, obtain mixed volume many solutions, and then push these all back after they've all become finite. So that's the big idea. I could do 5 lectures on the polyhedral homotopy. Okay. But it's a good theme to know is going on. So the theme that's going on is that if you have some parameterized polynomial system and you approach the exceptional set in a very particular way, you may see your solutions break up into buckets. And this might actually inform you about the structure of your problem. That's all I'll say about that. I will say, from a computational point of view, Julia's homotopy continuation.jl uses the polyhedral homotopy as its default. Okay. So you'll see this, and you probably already have as you've been using Julia. It says like using the polyhedral homotopy, or like mixed volume is this, or something like this. I can't remember exactly what it shouts at you when you saw the system, but it does this. Okay. Okay. Questions about it? Okay, and so what else did we talk about besides total degree families and sparse families? We talked about witness superset families. This is when you have an underdetermined polynomial system, so that you expect some large dimensional solution set. And the way you cook up a parameter homotopy out of that is you parameterize all appropriate dimensional linear spaces to slice your variety so that you get finitely many points. And those will, I'm not going to talk more about that because those will make an enormous appearance in a couple of weeks as our penultimate section in the course, and really where a lot of the meat of numerical algebraic geometry is. Okay. This is all great. And question now becomes, well, what if I have a really nice parameterized polynomial system and I want to solve? So I'm in some other situation, maybe. Maybe, for example, I'm looking at like 27 lines on a cubic, which we did in one of our first classes on computer. So there are 27 lines on a generic and okay, so that's by Salmon. And the thing is, cubics can be parameterized, right? I just have cubics, depending on some parameters, p is just a pijk times x to the I, y to the j, set to k, I plus j plus k has to be less than or equal to 3. Yeah, that's what a cubic looks like. And then lines in 3-dimensional space can be given coordinates as well, right? So how do you identify a line in 3-dimensional space? Maybe I can just talk about LBW as being some vector plus b times. Okay, so using the setup in one of our first classes, I think it was our first computational day, we wrote down equations for the lines which are contained in one of these cubics. Okay, so this was some parameterized polynomial system. So where did it live? All parameters were the PIJKs, and the variables, I believe, ended up just being V2, V3, W2, W3, because there's some redundancy in how we've written all the lines here. So it ended up being 4 equations and 4 variables, depending on lots and lots of parameters. Okay, so how do we compute the 27 lines? Is the whole point, right? So they're all cubics here. So by the way, the system we actually get is 4 cubics. Okay. So what is the Bezier bound of 4 cubics? Four equations, degree 3, 4 variables. Bezier says it has as at most how many? Three times 3 times 3 times 3.
So 3 power 4, 729.
Oh, was that?
No,
somebody?
81, I think.
81, 81. Yeah, okay, 81. So the next thing you should do, right? Because, pretend you're Sam, you have no idea there's 27 lines, you haven't written the proof yet, okay? You're trying to figure that out. Next thing you do is you might try to compute the mixed volume of this, and you'll get 42. And then the true answer is 27. Okay? So if all you know is this total degree start system, or this sparse polynomial system, this polyhedral homotopy, then to solve one of these, you're forced to waste either 15 paths if you're doing BKK. You'll only waste 15 paths. It comes at the cost of finding a start system for that homotopy is harder. So it does come up, it comes at a upfront cost to only waste 15. Or Bezier, which comes at essentially no cost because you can write down roots of unity like in 0 seconds. Okay. And then you would waste however many that is. Okay. Okay. 50. And so if you wanted to solve this problem for 1,000 different cubics, at first glance you might think, well, every time I solve it, I either have to choose to waste 54 paths or I have to choose to waste 15 paths. But that's not the case. And this really is the most important thing about a parameter homotopy, is that as soon as you get one solution set to a generic instance in your family, you can then use that one to get the rest. This is like a 2-step homotopy. It's a Texas dancing joke in there somewhere. Okay. Okay, so you got 27 to 1 map. Okay, you want to solve this one and you want to solve a bunch of other instances of this problem. what do? The first thing you do is you stick this one away from your parameter space of lines in three-dimensional space, and you throw it into either the Bezier or the BKK family. Okay, so that's going to land somewhere here. Okay, you have now interpreted the same polynomial system as a member of a different family. Okay. In your own lives, you belong to many different families, many different communities. Okay, and you have different relationships in each of them. Here, you've chosen a generic one, but in this family, it's not generic; it's special. You know, so this is maybe say BKK or Bezier. And why is it special? Well, it's special because over here, this polynomial system still has 27 solutions. But depending on if you're BKK or Bezier, this is either a 42 or an 81 to 1 map. Right? So it doesn't have the right solution count in this family. Right? So step 1, solve for the correct number of solutions and track that over count, either 42 or 81, to the 27. You'll waste some paths, but you only have to do this once. Because after that, after you have these 27 solutions, you just pick them up and you put them right back over here. There's still the 27 solutions of this very specific polynomial system in the correct family. Okay. And now from here, you can do a straight line homotopy to anything you want, and you're wasting 0 paths. So the cost of having to compute many instances of some parameterized polynomial system is going to depend on, well, how many solutions there are. Right? I'm definitely going to have to do like 27 tasks for every system I want to solve. I have to do 27 path tracks. So that's going to be like, so if I want to solve 1 million, that'd be like 27 times 1 million path tracks plus 81. The 81 only happens once. Okay. Upfront cost. Step 1. This is the parameter homotopy cost. A lot of times you want to do this second thing a lot after doing the first sequence. Okay. Any questions? If you lean toward thinking about applied problems and trying to solve them, then this is particularly insightful, I think. So a lot of things, say on your phone, you know, or on your computer, you want to solve some system many times. So I'm always reminded of this when I'm taking like a panoramic photo on my iPhone. Okay. What it's doing is it's taking many little photos. It's identifying common points in all the photos and it's gluing it together. Okay, so this is a problem in so-called computer vision. It's a problem that depends on polynomials. Okay. So maybe this problem has more than one solution, but they're trying to find like the best one or something like this. And so they have to solve something over and over again, the same kind of thing over and over again. It doesn't matter if you're taking a panorama of a beach or your friends or a party, like it's the same problem over and over again. So if I was designing this, I would keep some start solutions in every single iPhone and use those to solve the problem over and over again. Okay, now in practice, are you actually using numerical algebraic geometry to solve these computer vision problems? Not yet. Okay, but there's a large group of people who do work in applied algebraic geometry who think very hard about these computer vision problems, and they're ramping up the speed of being able to find these solutions really fast. So,
Do they use instead?
oh, they use some randomized linear algebra, I think, but I'm not gonna say for sure while we're recording. Okay. So super important to acknowledge how this all works in practice in this two-step. Okay. Amount of time. Any questions?
So, if you see a BKK bound, is there any chance of like without doing a actual homotopy continuation, is there any chance of figuring out how the parameter, the solutions, how many solutions should be there, how the system should look like?
So you're
Just-
saying, okay, so I write down these equations, nobody told me the answer was 27,
Okay.
right? Is that what you're saying?
Yeah.
Yeah, and I computed BKK, it's 42.
Yeah.
And if I'm interpreting correctly, your question is there any way to know whether or not this has 42 solutions without actually doing the path tracking?
Yeah.
Yeah, such a good question. I swear Deepak is not a plant in this class, okay? But I'm very, very excited to answer this question. We did not rehearse this. I only told you half of BKK's theorem. This is what I call BKK theorem is. And that's what most people know BKK theorem as. But it's stronger than that. BKK theorem actually also identifies exactly when you're on the exceptional set. So I'm not going to take class time to explain what this means. But I do encourage you to check it out. So like these are my polytopes, and I know what all the coefficients are. One thing I can do is I can pick my favorite direction and only consider the monomials, which are maximum in that direction. So then here and here. So if I forget about all the other coefficients of monomials, I get some system. It's called a facial system, corresponding to those two faces. Okay. Now you should not expect any of those facial systems to have solutions. This is essentially two equations in one variable over the terms. But if they do have solutions, that's why BKK is failing. If none of them have solutions, then BKK is failing. Counting multiplicity. Facial systems have solutions when there's solutions on
So,
boundary. Yeah.
one question. So, when you say a facial system, that means a pair of faces with one face could be could be any face of like, or does it have to be of any particular dimension, like codimension 1 or anything? But
So facial systems are parameterized by directions in the space. So the first thing I did to get this facial system is I chose a direction. And I solved the linear program of maximizing this linear function in this direction. So maximizing the dot product over this compact set.
okay.
Okay. So for example, if I chose up, right, then I would get this part and this part. But this part is just a monomial, and a monomial never has any solutions in the torus.
Right.
Okay. And so it's immediately clear that I definitely don't have any solutions in the up direction, right? And you can actually make this effective. So there are only finitely many directions you have to check. There are the normal directions of the Minkowski sum of all your polytopes. And yeah, I'm gonna move on now.
Okay, sorry. Yeah.
Okay, yeah, no, don't apologize at all. But yeah. Talk to me more. This is like what my thesis is about. So
Mm.
okay. Moving on.
So, what you just answered is like when you can say that if it is not actually true, solution set is not 42, then you can say yes. Okay.
Yeah, and if I can actually count the number of solutions, so the number of solutions in these boundary divisors of the appropriate toric ring, so by checking the solutions in the spatial systems, and if I can count them, which one may not be able to do, but if you can, then that will be the difference.
Ah, right, okay. Nice.
Okay.
Wow.
I think one has to be careful about whether or not you have like positive dimensional solution sets in a facial system, because then I think you don't really get a count. Right, so you would still have to be lucky to be able to identify this difference.
Okay.
If you're familiar with projective geometry, like you know that Bézou's theorem, if you've done algebraic geometry, what it really says is that two curves that don't share a common component of degrees A and B have exactly A times B many common zeros, counting multiplicity in projective space. Not generic, always, as long as you're not sharing a component, right? We only get this generic result because we've been working with an affine space, so just a C to the n this whole time. We haven't really talked about projective space. But this is hidden behind this vague notion of running to infinity, right? So if I move this line vertical, this point goes over here, this point flies off to infinity, right? And you'll notice there's only one solution here. Well, that's because the other one is hiding at infinity. So if I actually worked in projective space, I would be able to see both solutions at infinity. And the failure of this system to meet the Béziou bound is exactly encoded by how many solutions went to infinity. So one thing you can do is you can count how many are at infinity, if you're lucky, and then subtract that off of your bound and get the true count. But you can't always do this. It's a little bit so. It's a lot so. Okay, so we talked about these very general setups depending on the monomials appearing in your polynomial systems for how to cook up parameter homotopias, namely Béziou, BKK, anchored the witness set problem for later. But I want to talk about one more instance where you might see a parameterized polynomial system showing up a lot, and that is in the context of optimization problems. Okay. Concerning polynomial optimization, asks to optimize some polynomial function over some variety and let's say this is a prime ID, generates a prime field. You don't love thinking about prime ideals, that's fine. You should just think of this as like Alex hasn't taken your polynomial system and screwed with it until it makes stuff break. Okay. I just really want a good generating set for the equations which cut out an irreducible variety. Okie doke. Optimize. What the heck does that mean? Well, minimize or maximize. Okay. So I can think about this like that. Think about this as actually being some real part of an algebraic variety. And I should probably think about this as a real. So I can talk about maximizing. I can't take the maximum of a bunch of complex numbers. Okay, but don't worry, the real stuff's gonna disappear in 2 seconds. I mean, that's the thing. So let me have a variety. This is my variety. And let's say I want to like have some vector v, and g is just take the dot product of u elements. So every point, so maybe this is the origin. At every point, there's some line perpendicular to that vector, and g is just measuring the distance of that. Probably g squared. No, g is square root of g is distance. So if I want to optimize this, okay, so what do we do in calculus when I want to optimize something? Right? Okay, so the problem comes as like minimize or maximize, but you don't even care about minimizing or maximizing as soon as you take your first step in calculus. You care about finding the critical points, right? Care about finding the critical points. So you're setting some differential information equal to 0. For us, with this example, critical points are happening there. And how do I identify these so quickly? Well, the tangent spaces at these places are they are perpendicular to the gradient of this function. I can also, for example, just choose my favorite point here and talk about the distance from this point. In which case, these will kind of be my level sets, and then, oh, there's one, right? And so the gradient here is going in these directions of this function. And the critical points are when they're perpendicular to the tangent space of your variety. And your optimum are amongst your critical points, just as they were in calculus. This is essentially like Lagrange multipliers. This is the idea behind Lagrange multipliers. So we're just going to soup up Lagrange multipliers for our setting, and they're going to be called the KKT equations. Okay, so if I'm going to have a critical point, first and foremost, it better be on my variety. Okay, so first bucket of equations I have is the actual defining equation. But the second is me asking that the gradient is perpendicular to the tangent space. So I'll write the gradient as this. It's just all you're doing. I'm going to include new variables. You've seen this from Lagrange multipliers. And essentially that's that the gradient of g is a linear combination of the gradients of the f's. Let's unpack why this is the same thing that I told you over here about the tangent space. So the Jacobian of F is a k by n matrix. which is also known as like this. So kernel is tangent space at some point. Row space is perpendicular to tangent space. So I want to ask that the gradient of G is in the row space of this. In other words, it's a linear combination of the rows. Okay. How many equations are there in total between 1 and 2? A from here and n from here, because this is, notationally a shortcut to describe n equations. So n plus equations. And how many variables? Well, I had n to start with, my xi's. How many lambdas did I have to include? K. So you write down these KDAT equations, you'll always have a square system. And that means if you parameterize some family of optimization problems, you have a square parameterized polynomial system, and you get to do parameter. Okay. Any questions? These show up everywhere. Oh, maybe one remark. This may include singular functions. So for example, I have a variety that looks like this. And I like try to optimize this direction. Yeah, I'll pick up like this point, and this point, because these are the, well, and maybe there too. But I'm also going to pick up these two points. The equations kind of pick those up just for free, because the Jacobian doesn't play nice there. Okay. So you throw those out. Good. Okay. So a lot of times in applied algebraic geometry, you have some variety whose points are describing some physical phenomena that could happen. For example, so you have some variety. But you're an applied scientist, so you actually went out to the real world and you collected data. Okay, you collected data that you think should lie on some variety. But it's data, so it's never perfect, so it's always wrong. You get some point that's not on your variety. Okay. What's the natural next question if you're trying to solve this applied problem? So data, it's not on your variety, but you know the truth has to be on some variety. You want the closest point on the variety to your data. Okay. Let me give you an example. No, before I give you an example, U is, well, the distance between a point and U. Minimizing a square root is the same thing as minimizing the thing without the square root over the roots. So since square root doesn't give me a polynomial, this does. Okay. And so now we're exactly in this situation where we have these, we're trying to maximize or minimize distance from you. Okay. And how do you do it? Well, you find all the critical points of AKT equations. They depend on the point U as your parameter. So as you move U around, you'll have different critical points. Your X's and your lambdas. And of course, you don't really care, right? You want the X values, which are critical points. So this is the Euclidean distance problem. And since this is a square parametrized polynomial system, it has some generic number of solutions guaranteed by the parameter continuation here. And that number of solutions gets a name called the Euclidean distance degree of X. And the more you think about these kinds of problems, the more you see them pop up everywhere. Right? Ah, somebody gave me a square matrix. I want to find the closest matrix which has smaller rank, or the closest matrix which is an orthogonal matrix, or something like this, right? Like these things happen all the time. You know, and some of your linear algebra algorithms actually do this. So. Okay. Questions? Okay, so at this point, I'm going to take a pause for the next 7 minutes. Think about whether or not you want to see more examples here or more examples on the computer, and I'll let that guide the second half of today. Okay. All right, see you in a bit.